Right. So, good afternoon, everybody. My name is Olivier Grisel, and this session is going to be about machine learning in Python with Scikit-Learn. So, this is the kind of sequel of the session from this morning by Jake, who is over there at the back of the room. So, we will go in a bit more details. And the material for this tutorial is available on my GitHub account under Paul ML tutorial. We are not gonna cover the Paul part in this session, but I'm reusing an existing repo. But if you're interested in that specific part, it was presented at PyCon a couple of years ago and was recorded. So we will cover stuff that is complementary. There is a bit of overlap, but if you're interested in the other notebooks, you can also have a look at the video. So I hope that you had the time to install IPython notebook and specifically maybe from the Anaconda distribution, because we will need in this session Scikit-Learn, pandas, IPython notebook, and the NumPy, SciPy, Matplotlib ecosystem. So who has not those software installed and running on their machine yet? Because I have a bunch of USB keys, so if you need the keys, okay. It's much faster to install it from that. So.
I'm actually having some issues with the way that it's showing up on mine, so I can help you.
Yep. Okay. So Jake is there. If you need help, if you're stuck with a setup issue or a technical issue, you can ask him. All right. So once you have IPython notebook installed, you should run it. So for instance, from the console of your system, you can type IPython notebook in your home folder and navigate to the folder where you downloaded Paul ML tutorial. And you can open the first notebook so that we can test that it's actually properly installed. So while you're doing that, let me introduce myself. So I am a software engineer in a research institute in France, in Paris, which is called INRIA, and we are doing research on the brain using fMRI data to try and understand the structure of the brain activations with respect to stimuli like visual or audition or movements and stuff like that. And in that team, I am responsible for, I am a software engineer, basically I'm not a researcher, and I'm working on the Scikit-Learn project as a contributor. So this is my job to help maintain the project and move it forward. So today, let me switch to the notebook. So once you have started IPython notebook, you should go to the folder, the Parallel ML tutorial folder, and you will see two subfolders, notebooks and rendered notebooks. So today we will use this one, notebooks. But if you want to follow along without executing stuff, you can use the rendered notebooks also from the nbviewer website. For instance, if I go to nbviewer.org and you type Grisel Parallel ML tutorial, let me make it a bit bigger. You can see from the nbviewer website the same kind of listing, and this time you can go to render notebook and you have access to the tutorial material in a static manner. So it's good, you can see the output of the execution already computed here. So it's just a static website generated from the notebook. But today we are gonna execute stuff, especially if you want to do the exercises. So in your localhost Jupyter Notebook or IPython Notebook, you will go in the notebooks folder. Okay. And in the notebooks folder, you will see those notebooks. All right. So today we will cover 3 of them. The first one is number 4, pandas and heterogeneous data modeling. Then we will see number 5, model selection and assessment. And finally, we will have a look at text data with the notebook number 7. So basically, the previous notebook tend to overlap a bit with Jake's session, and there are actually some material by Jake here. So the goal of this session is to see 3 different practical issues that you need to be aware of when you're doing data science or predictive modeling in general. The first point is how to deal with heterogeneous data. When I say heterogeneous data, I mean data that has different columns with different data types, when it doesn't naturally fit in a single NumPy array. So how to massage your data using pandas to make it fit into a regular NumPy array so that Scikit-Learn models can accept it and work correctly. Then we will deep diver into model selection and assessment. So this is a bit more theoretical. We will focus on how to properly evaluate the predictive quality of a trained model. So which methods and tools from Scikit-Learn we can use to do that in a generic manner. And we will deal with stuff like overfitting, underfitting, and how to fix those statistical issues. And finally, so we will do a break in the middle. I don't know exactly when. I think it's at 3. And finally, we will have a look at text data. So text data is not numerical data by default. So we will see that we need to do apply a bunch of techniques to make it possible to train machine learning models for classification or maybe for clustering on text data. And so we will have a look on those issues at the end. So text classification can be, for instance, sentiment analysis or topic detection, for instance, in blog post, or if you want to recommend news articles to a specific person based on a previous navigation history. All right. So let's open the first 0.0 tutorial setup to check that we have the software correctly working. So here I'm using Jupyter. You might be using the previous version of IPython, which is IPython 2.3 or 4. Jupyter is the new version of IPython that is not specific to Python. It has been generalized a bit for working better with programming languages like Julia or R or Haskell or Scala or whatever. And so you see that the format of the notebook has changed. So to make it easier for everyone to follow, I have the previous version of the notebook loaded by default. But if you have the latest version of Jupyter, it will convert them when you execute them first. All right, so let's hide this. Okay. So this is an executable document. So you can follow along by hitting the Shift-Enter key, and you will see that the cell under focus is moving each time I do that. So Shift-Enter. And here you can see that I have input number 1, that there is a prompt number that has changed because it has executed that Python cell. So you can execute those and check that you don't get any error message. Then It's useful when you import NumPy, for instance, this library here. You can also put numpy.path here, and you will see where it's installed. Actually, I'm running Anaconda. Okay. Those notebooks should work both with Python 2 and Python 3. And you can see the version using __ version. So we will need some data at some point, especially for the text part. So you can execute that cell to fetch the data from the internet. And it will take some time the first time. It's a couple of megabytes, should be quite fast. And once it's downloaded, you should see the 20 news groups datasets. You might not see sentiment 140, but you don't care. All right. Does anyone has any issue with importing the libraries? Yes. What? The first three? What do you mean? Okay, okay. So it's all right. If you see 20 news groups and Titanic, maybe no. Weird. Maybe try this. I don't remember. No, I don't remember how I did it. Okay, that's not a problem. We can download it later. Or maybe I moved it somewhere else. So it's an older copy that I have here, I think. We'll see. Okay. So I assume that everyone is familiar with NumPy. Is it the case? Does anyone does not know NumPy here? All right. A couple of people. So we can just do a quick overview of NumPy first. So NumPy means numeric Python. It's a library for a linear algebra manipulation, numeric data analysis in Python. Basically, it's an abstraction for a data structure that is called a NumPy array that makes it possible to deal with high-dimensional data. So first, we can create a NumPy array with 3 elements, 1, 2, 3, so integers, in a variable named a. And so in that case, those are just like a list of numbers. But b, you can see that we have 2 dimensions because we have a nested list. And in that case, the default representation is two rows and 3 columns. So we can have a look at the shape attribute of B, and you can see that you have the number of rows first and then the number of columns. And you could have an arbitrary number of dimensions. It's not restricted to vector and matrices. It can be anything. So NumPy arrays have a data type. So this is very important. So in that case, we used integer numbers by default to fill the cells. So you can see that it's a 64-bit integer for A. And A also has the same data type, but the shape of A is different. It has a single dimension with 3 elements. We can create an array of zeros, and by default, the data type of this guy is float. I can type the type here. Float 64. You can see that you have the precision. We can also create an array of ones and with a specific shape and a specific data type here. So it's a 32-bit integer, so less precision. So NumPy arrays are very nice because they provide a high-level API to manipulate to do array operations. So for instance, if I take my array B, so it had those values in the beginning, I can divide the value by 2 by multiplying by 0.5. And I will get those values, and you can see that the shape is still the same. I applied the element-wise operation, a multiplication, element-wise multiplication to all the cells of the B array to get the C array. So the shape is still the same, but because I divided by 2 using a floating point operation, the data type has been changed automatically to a float data type. I can also add two arrays with the same shape or with compatible shapes. So you can see here that C has 3 columns and 2 rows. A has 3 columns and 1 row. If I do A plus C, you have this behavior which we call broadcast, and A will be added to the first row of C and to the second row of C, and we will get the D result. We can also access the elements of an array. For instance, I can access the first row of an array by using an index like this. I can use 2 indices to get a specific cell. So for instance, the first column of the first row. And I can also slice a specific column. So I want the first column and all the elements of of all the rows that match that column. And you can see that this is those 2 values here. So the result of that guy has shape 1D, 2 elements in 1 dimension. We have also the basic operations like the sum and the mean of elements in that array. The mean is the average value. You sum and you divide by the number. And we can also compute the sum along a specific axis, so along the rows. So for the 3 column values, we have the sum of the mean of the columns. And we can also compute the average along the columns. So for the 2 rows, we have the mean values. Under the hood, NumPy is using a very efficient implementation of matrix or vector operations. So it's continuous chunk of memory. So it's not using individual Python object to represent the different numbers. So it's much more compact in memory, so it's much more memory efficient. And it also provides additional operations that are implemented by Fortran libraries like BLAS and LAPACK operation for matrix multiplication, for instance, or singular value decomposition. And so it's much better to use NumPy when you can, rather than trying to re-implement stuff in Python or in C, because it's probably it's very likely to be faster by reusing the existing NumPy routines. NumPy arrays, you can also modify them in place to avoid allocating a new memory. So for instance, here I allocate a range of integer values between 0 and 11 as a 1-dimensional array. I can reshape it as 3 rows and 4 columns. And you can see that F is actually a view on the content of E. So it's the same data in memory. And when I modify the 5 last values of E, so you can see they have been set to 0. The matching elements in F have also been set to 0. To understand that, you can have a look at the flags, F flags. And you can see in particular that F does not own its data. It's actually a view on a different array. So this is very important to keep in mind. So specific operations like slicing and reshaping arrays are very cheap because they don't allocate any new memory. They are just providing a view on the same chunk of memory under the hood. You can also combine arrays, for instance, by concatenating them. So here I will concatenate A 3 times. So A is a 1-dimensional array, so it will concatenate along the same axis. You can vertical stack arrays that have a matching number of columns, and it will use broadcasting when needed to do that automatically. So here we have the values of A, then we have the values of B in those 2 rows, and the values of D here. And you can see they have the same number of columns, so it works. This is doing a new memory allocation because the result has a different size. And the same is true for that guy. We can also do horizontal stack if you have the same number of rows between B and D, and we get this. So this is very useful because in machine learning we will manipulate data sets, and usually the input data for machine learning models is two-dimensional, so it's very useful if you want to enrich to add new features, we will see later. You can use HStack to concatenate features, and if you have different chunks of the same data set, so with the same number of columns, you can concatenate them in a contiguous array in memory. So finally, we will also use a lot of matplotlib to visualize the data. So here I'm creating first the first array. Let me change that a bit. Okay. X with values between 0 and 2, and I want 10 values equally spaced. I can plot those values using the plt plot function. So you can see those are my two values between 0 and 2. And here, by default, on the x-axis, I have the index of the values. I can also do a plot with x passed as the x-axis and as the y-axis. And you can see the blue line here is my x function, my x data. And I can compute the squared values of x and plot them as the y value on a second plot with a different label, and put a legend, which is here, put a title, which is here, and label the axis as input and output, and I can see the two functions. So PLT plot is very useful for visualizing the relationship between two variables. But something that is even more important is visualizing a distribution of values. And most of the time you can use histograms. So here I'm generating random values using NP-random normal. So it's a Gaussian distribution, a sample of a Gaussian distribution with a mean value of 1 and a standard deviation of 0.5. And I want to sample 1,000 samples. So I get a NumPy array with 1,000 elements. The values are floating point values. I can have a look at the first 30 elements, and but it's not really easy to see the distribution of that data, so we can use PLT-hist to see an histogram with 50 bins, and you can see that it looks like a Gaussian variable. It's also interesting to do to compare two distributions on the same plot. In that case, you can use PLT-hist twice on the same plot, but in that case you should put an alpha value of 0.5, for instance, which will change the opacity. And if you want to compare two histograms on the same plot, it's better to compute bins for the two histograms ahead of time so that they are aligned. Oops, I forgot to generate the data. And you will see the two distributions. So the samples from my student T distribution and the samples from my Gaussian distribution. Finally, when you have two variables, you can also scatter plot them, and it gives you an idea of the spatial arrangement, the 2D spatial arrangement of those samples, of those two variables. Yes, you have a question? ND assignment for the plot? Yes, those guys. It's just that actually in that case there is no problem, I think. But if you have, if I comment this guy, what? This is weird. I did not expect that. Or maybe it's because of the comment here. Yes. When you execute matplotlib functions, by default in IPython notebook, matplotlib will return objects that describe how it computed the plot, so that you can manipulate those, like for instance, to stick a new axis or a color bar. And especially for histograms, it's very verbose. And you still have the output, but then you, in the IPython notebook, you see that. So you have two options to get rid of that. Either you stick a semicolon at the end, and that will return none, because it's a Python statement, so it's a hack that hides this. Or you can assign it to the main variable and get rid of it this way. Let me put back my legend. Okay. All right. Okay, so now that we have the basic matplotlib, we can, and NumPy, we can try and use pandas, and not use NumPy again. Joking. All right, so let's open notebook number 4, pandas and heterogeneous data modeling. Again, I will hide. It's converting the notebook. We'll hide this. Sorry. Okay. So don't forget to execute this first cell, because we will need it later. So this first cell actually is using the matplotlib inline magic here, which means that when you use matplotlib, we will not try to create a new window on your operating system, but we'll include it in the output of the notebook. Then we import the classical libraries like that we will use. Matplotlib, we use the alias PLT. For NumPy, we use NP, and for pandas, we use PD. So those are classical aliases that many people in the scientific Python community tends to reuse. Also get rid of some deprecation warning depending on the version of Scikit-Learn that you use. So when you do data science and predictive modeling in general, you tend to follow this data flow. You first start from the original data, and this data can come from an arbitrary database or a file system or some API of a web service, for instance, a REST API. And they can represent different kinds of digital artifacts, like for instance, text document, images encoded as PNG or JPEGs, sound recordings in MP3, for instance, or transactions in a log, in a text log, or in a database, or in JSON file. And when you're doing supervised machine learning, you want to predict the value of a target variable. And this variable, when it's not naturally there in the original data, you need to label it manually to hire people on Mechanical Turk, for instance, to label what's inside the images. Do they hear some specific sound in a recording, or the kind of music that the recording is about, or stuff like that. So for each element in that database, you will need a specific label. To be able to apply machine learning algorithm, you will need to find a common representation, a numerical representation. Most of the machine learning algorithm in Scikit-Learn expect a two-dimensional array of numerical values as input. And the columns of that array are called the features, the numerical attributes that describe each specific row. So when we come from the original representation to the NumPy array that we will feed to Scikit-Learn, we will need to do this blue arrow transformation here to extract the feature vectors. And the goal of this first notebook is to explain how to do that for a specific kind of elements, which are transactions, for instance, in a CSV file, where the different columns in your CSV file or in your database have different data types. For instance, you can have dates, string values, numerical values that have different heterogeneous types. So we see that we can use pandas to do this transformation. Once we have the numerical description, we can use arbitrary machine learning algorithm from Scikit-Learn, and it will produce a model, a predictive model. And once we have this, we can ingest new data on which we will apply the same transformation to produce a prediction, the expected label. So to do this exercise, we will use a standard data set that is used to teach data science. So it's an open data set of the passengers of the Titanic. So it should be in the same folder, so you can try to execute that. So we will open the file and zip through the five first rows, and print the lines. So can you do that? If you have errors, please raise your hand. Nope, okay, it's fine. So you can see that it's a CSV file. If I zoom out a bit, I have different rows. Okay, not lucky with the resolution here. But you see on the first row we have the names of the columns, and then we have values. And the first three columns, they have numerical values. And some of the columns have those quotes for text values. So you can see we have heterogeneous data. So the best way, or the easiest way to load CSV data in Python is to use pandas read CSV. So let's use this. And what we get back as a result is what we call a data frame. We can call the head function on the data frame and get this representation of the data frame. So because we are in the IPython notebook, we have this HTML table as a representation. But internally, it's just a Python object that has the data loaded in memory. So you can see that we have 2 dimensions. For each column, we have the name of the column that has been parsed from the CSV file. And we have an additional column that doesn't exist in the CSV file with the integer number of the row, which is used as an index to access the data row by row. So here we cannot really see the data types, whereas they could be integers or floating point values or strings and so on. We will see later how to do that. The first operation that we can do on a data frame is count the non-zero, the non-missing values of each column. And just by doing so, we can discover something weird about this data set, is that for the passengers of the Titanic, we just have 714 people with ages, whereas in total we have 800, almost 900 people. For each of those person, we have a specific ID, an attribute that says whether or not the person has survived the crash. Then we have the class of the person. The class is an integer value between 1 and 3, first class, second class, and third class. And then we have the name. And you see this is the full name, and there is some variability because sometimes you have nicknames or stuff like that. Then the sex, which is a string male or female. Then the age, which is a number, and some of them have missing values. Then we have some information on whether or not there were siblings and parents, I think. I don't remember. We would have to read the documentation on the website. With the person on the Titanic. Then the ticket number. Then the price they paid to get their ticket. Their cabin number. And you can see that we have a lot of missing values for the cabins. And finally, we have the port of where they embarked. And there are 3 possible values for that column. Let me scroll horizontally if I can. So we have Southampton, Cherbourg in France, and we don't see it on the first 5 rows, but there is a third city, Queenstown, I think, with the letter Q as the symbol in Ireland. So if you want to get the details on what those features, those columns mean, you can see on the Kaggle website where they have a competition that uses this data to try data science, and they have a full description of the data set. So on the data frame object, on the pandas data frame object, you can access the columns. And this is just if I take a list, just a Python list of strings. But by default, it's a weird pandas index object that can be used to slice the data frame. But what is interesting is the name of the columns. I can also access attributes that looks like NumPy arrays, like the shape of the data. So it's a two-dimensional array, a data frame. And I can actually convert it into a NumPy array by calling the dot values attribute. So you can see that what I get as a return to that function, it's not a function, it's a property. I get a real NumPy array with a specific data type which is called object. And object means that I can have any kind of values there. So in particular, there are numbers and there are missing values and there are strings. So it's a big mix. Most machine learning algorithms, they don't like this kind of heterogeneous data. So even though it's a NumPy array, Scikit-Learn will complain about it if you feed it the data frame or the values array directly. So the goal of this session will be first to identify the column that we will use as the target variable, select some attributes that we will use as input features, as descriptors that can be predictive of the target variable. The target variable that we will use here for this exercise is the flag that says whether the person has survived or not. And there are some attributes that have no predictive values, like the ID, the passenger ID, which is unique to each person. So there is nothing we can generalize from unique values, so we can get rid of it. And finally, we will extract a numerical representation from columns that are not numeric by nature. So that we call categorical variables, for instance. So first, we will extract the target variable. So in a data frame, you can use this operation, that looks like a dictionary, Python dictionary access. But what we get as a result is a specific pandas object, which we call a series, a pandas series. So you can see the class name. Whereas the original object that we had is a data frame. So you can see a data frame as a collection of series, and the series are the columns of the data frame. We have some similar operations on the series that we have on the data frame. But first, we can use the group by function on the data frame and use count, and we will see the two different possible values for survived, and we will count the number of values, non-missing values that we have for the other variables. For instance, here you can see that the age column is approximately balanced between the two target classes. So the survived column, we can see that it's not balanced. There are many more people who died than people who survived, and we can use NumPy to compute the likelihood of surviving the Titanic without any additional value. And actually, it's the likelihood of dying, and so you can see that 62% of the people on the Titanic died, approximately. This is actually a subsample of the full data set, so this ratio is an approximation. So we have this target column here, survive column. We can call the values attribute on a column, and we get back an array, a NumPy array, with a fixed D type. So the columns themselves, they have a data type, and inside the column, you are guaranteed that the data is homogeneous. So we can convert it into an array, it's going to be clean. We can have a look at the first 5 values, and you can see that we have the 0 and 1 markers that we had previously here in the survived column. So we will get an NumPy array with those values, that specific column. Okay. Okay. So first, we'll start to do a machine learning to try and predict this variable, the survival of the person, by just using a subset of the columns that are already numerical by nature. So we can slice the columns that we are interested in by using this double squared bracket operation. Basically, we pass the list of string names for the columns that we are interested in, and we will get a new NumPy, pandas data frame that is restricted to those columns. So it's a subselection, horizontal subselection. So you can see that they are all numerical features, and you have a natural ordering relationship between the values. For instance, you have high prices and high classes and low classes, and people that are older or younger. There is still an issue with that data, is that we have missing values for the age attribute. So the possible way to deal with that case, most machine learning algorithms in Scikit-Learn will complain if they have missing values. So we need to find a way to get rid of them. So we have 2 possibilities here. We can either just drop the lines that have missing values by calling the drop NA operation, and you can see that we get a data frame as output, and we can count the lines, and we can see that we are just getting rid of the people who have a missing age, but we are getting rid of the full rows. So we are losing some data on the fare and the class of those people. So the second option that we have is to compute the median price and the median class of the people that have non-missing age, like this way. And you can see the price is $15 on average, and the class is the class number 2, second class. And actually, we don't care about that. What I was interested in is the median age, so 28 years old for the people that have non-missing age. And we can reuse those median values and replace the missing values with the median values whenever there is a missing value. And if we do that, now we have all the passengers have an age. It's just that some of the passengers are marked as 28 years old, even though it's not true. But it's a reasonable thing to do because it's in the middle. We could have used the average age instead of the median, but median tends to be slightly more robust to outliers. For the age value, we don't have much outliers. So it's likely to yield a very similar result. We can actually compute the mean if you want to have a look. And the average age is 29 instead of 28, so it's not a big deal. All right. So now we have a new data frame, which we call imputed features. And we can check that all the values, we actually checked previously that all the values are non-missing. So now that we have a NumPy array with non-missing values, with no missing values, we can convert it as the NumPy array. We have a data frame that we can convert to a NumPy array. And this time, the data type is floating point values. There is no longer any object data type. So we can use machine learning models on that data. So to be able to do proper machine learning, we will first split the data set into a train part and a test part so that we can train the model on the training subset and evaluate the predictive accuracy of the model on the test subset. So to do this split, we will use a function from Scikit-Learn, which is called train test split. And you can see that here I am calling this function by passing two arguments. The first one is the input array that I just generated from the features. The second argument is the target variable. And then I have parameters like the fraction of the data that I want to use as test data, and an integer seed that controls the randomness of the split. So all the splits will be random, so I will shuffle the data before splitting. But to get reproducible result, I can fix the seed using the random state attribute here. So when I do that, I will get four resulting variables. The first two are the input features that have been splitted into a train and test part. And then I have the target that has been splitted in train and test using the same indices, the same separation. So I can check the shape of those four arrays. And I can see that for the input value, I have two-dimensional data, and I have a bit more than 700 passengers in the training set, and a bit less than 200 passengers in the test set, and the same number of labels for the train and test targets. All right? Do you have any questions there? No? Okay, so we can call logistic regression on that data. So logistic regression is a classification algorithm from Scikit-Learn. We just pass a value for the hyperparameter. We fix it to c equal 1 for now. And we call the fit function on those two NumPy arrays. So this will train the model, and it returns the model with the updated internal parameters. Once I have a trained model, I can call the predict method on that model, and I pass as an argument the test features, and I will get some predictions. I can have a look at the predictions if I want, and you can see that I have 0 and 1 values, whether or not the person has been predicted to die or to survive. So once I have those predictions, I can compare the predicted values with the true values. And I see that in that case that I have 73% accuracy for this prediction. So this is not very good, but this can be explained for two reasons. First, we are using a very simple model, which is called logistic regression, so it's just a linear model. And second, we have just used 3 variables out of the full data set. So we have not leveraged all the possible values. We can compute the score and on the model, and it's actually just a shorthand for the accuracy. Once we have trained the model, we can try to see inside the model what it has learned. And to do that, we will have a look at the coefficient attributes of the fitted model. So coef is actually storing an array of weights, one weight for each possible input feature. So in that case, I have 3 input features, the price, the class, and the age of the person. And we are trying to predict whether or not the person has survived. And you can see that the higher you pay for getting into the Titanic, you have a positive correlation with the survival. So it means that people in first class, which is actually stated here, first class is lower than third class, and you have a negative correlation with survival. So it's compatible with the price, and the age is negatively correlated with the survival, or negatively weighted, and this means that rich people and young people, so rich children, had a higher likelihood of surviving the Titanic. And it's actually matching the what we observed, because the upper class cabins were closer to the lifeboats, and it's likely that the children were given a priority to get into the lifeboats, whereas people from the third class were at the bottom of the ship. It was much more complicated to find some spare lifeboats when they could reach the upper deck. So this is kind of confirming what we observed in real. So the coef attribute is always there for linear models in Scikit-Learn. So it's a good way to see how the decision is taken by the model. In practice, it's just multiplying the price by this weight and then summing it with the multiplication of this weight with the class number and summing it with this weight with the age. And if this value is positive, the model predicts survival. If it's a negative, it predicts death. We can also do a graphical representation. And you can see that the fare is slightly positive, p-class and age are negative. Here, the absolute values don't really mean anything because we haven't scaled the input features. But anyway, we have a high correlation between the fare and the class. So we shouldn't interpret too much the values of the coefficient because of that correlation, because it could be misleading. All right. Yes, question?
So are some of the fares also higher because they're like closer to the window or whatnot? I wonder if how like are they collinear?
Yeah. So I don't. So the question is, why do we have different fares? It might be because specific cabins where even they were first class, they had differences, and maybe because also they had specific deals. I don't know. But there is a strong correlation. I haven't computed it, but it's strongly correlated. So another way to evaluate the quality of the model, besides just computing the accuracy, is to display the confusion matrix. So the confusion matrix compares the predictions with the true values, and you see on the rows of that matrix the true values, and on the columns the predictions. So here you can see in the diagonal the correct predictions, so the true positive and the true negative. I don't remember. No, I think the survival is on the second row. So the true positive 33 and the true negative 98. And you can see false negative here and false positive here. So we can use matplotlib to make that more explicit by putting labels on the axis, survived and not survived. Yeah, I switched the order with the... Oh no. Maybe I made a mistake here. Confusion matrix. Yes, I think this should be not survived first and survived later. Okay, I fixed that this morning and I made a mistake. Okay. Anyway. So not survived and then survived. And it's also possible to normalize if we want to have the false positive and the rate and the true positive rate and so on, by computing the sum along the rows, the sum of the values, and by dividing the confusion matrix by that sum. And I need this specific slicing here because I want to have the right shape for broadcasting, for NumPy broadcasting. And here we have the true negative rate and the true positive rate, and the false negative and false positive here. So I can also do a graphical representation, and I have the same problem for the targets. I need to change them. Actually, it's correct there. Okay. Okay. One last utility function from Scikit-Learn that can be useful for evaluating the quality of the model is the classification report function. So you need to give it the target names and the predictions and the true values. And it will compute 3 different kinds of scores: the precision, the recall, and the F1 score. So if we consider survival as the positive class, precision is out of all the prediction that I predicted as positive, how many of them are real positives. Recall is out of all the passengers that should have been predicted positives, how many of them did I got it's the ability of not forgetting people, basically, and precision is the ability of not predicting negative stuff on positive passengers. And F1 score is some kind of harmonic average between the two. So basically, if you are very bad at precision or at recall, you will have a F1 score that is bad. Why do we use that instead of accuracy? Maybe you have an idea. Why is it better to use F1 score in that case than accuracy to evaluate the quality of the model? Yes? Yes, the answer is imbalanced classes. You can see that we have many more negative values than we have for positive values. So it means that if you push that to an extreme, like for instance, if you have 1% of the data that is positive, and 99% of the data that are negative, just predicting negative constantly will yield an accuracy of 99%, even though your model is just predicting a constant value. So it's much better to take that into account in a score that makes it hard, even when you have imbalanced data. All right. So there is also another attributes of the logistic regression model that is interesting, is that you have this predict proba function method, and what it gives as a result, instead of getting a hard prediction of positive survival or negative death, you have some estimated probabilities of survival. So the second column here is the estimated probability. So for the first passenger, it will predict death because there is only 25% probability that it's going to survive. So you can use the predict proba output of logistic regression as some kind of confidence level of the model. And it's also useful to be able to plot what we call the ROC curve, which makes it possible to see the behavior of the model when you change the threshold for the decision function. And so a random model on this curve will be very close to the diagonal, and good models will be very close to the top and left axis. And so if you plot different models, competing models trained on the same data on the same plot, you can see whether they are for a given level of false positive rate, what is the true positive rate of that model, which is also called the sensitivity, and on the x-axis, it's the opposite of the specificity. So it's another way of evaluating the model. And you can compute the area under that curve, and in that case it's 0.756, which is a good metric also when you have imbalanced data. You can compare, it's an alternative to F1 score, for instance, when you have imbalanced data. So you see, up until now, we used a specific train test split. And previously, we've used random state equals 0. And we trained the model and we computed the accuracy. And we got 73% accuracy. If we change the random state here to 1, the seed of the split, of the random split, and we train a new model on that new training data and evaluate it on the new test set, we see that we have a very different target accuracy. And if we change again, we see 66, 67. So we were actually a bit lucky in that case, because the split that we used is apparently quite easy to get a good accuracy. But with different splits, the model can be much worse. So it's to take that variability into account when we evaluate the model. It's good to do several iterations on that train test split. So to do that automatically in Scikit-Learn, we can use a function that does cross-validation, which is called cross-val score. It will basically split the data into 5 folds, and will keep each time one of the folds as the test set, and will concatenate the 4 other folds as the training set. It will train a model on the training set, evaluate it on the test set, on the validation set, and output the score. And it will do that 5 times, and we get the scores as an outcome. So you can see those 5 scores. We can compute the mean, max, and average. And you can see that on average we are a bit below 70% accuracy. And there is some variability between the two. The cross-val score function is also very nice because it makes it possible to directly compute the area under the ROC curve. So to take into account the fact that we have imbalanced data. And actually in that case the value is slightly higher, but it doesn't mean the same thing. So it's a 0.72 area under ROC curve. And you see that there is a wide gap between the mean score and the max score, so the randomness of the split is actually impactful. So let's try to play a bit with this. So try to use the cross-val score function to compute the precision and the recall, the F1 score, the accuracy, and try to change the number of folds of cross-validation and see the impact on the score and maybe on the processing time. So I'll give you 1 minute. Yes. Where is the second USB stick? Okay, thanks. Okay, so let's do this. So the first exercise is to change the kind of scoring that we want to compute. So we can just use precision, and it will use a different function from the metrics module of Scikit-Learn to compute the precision. We can do the same for the recall. And you can see that the recall in that case is much worse. F1 and so on, it's the same. So let's keep F1 for instance. Now we can change the number of folds of cross-validations. I can use 3-fold cross-validation. And I see that the score is slightly worse. The average score is slightly worse than with 5. If I increase to 10, it's getting better. And what I can do also is use the person time magic in IPython. So actually I don't get the score as an output, so I need to print it. So when I put person time, I can see that I have the execution time as the wall time displayed below the output of the cell. So if I change, so here I get, if I execute it several times, I can see that it's around 30 milliseconds, so it's very fast. I'm not sure we see anything. Actually, we see. If I change and I put 3, I can see that it's much faster. So can someone explain why the speed of the cross-validation is much faster when CV is small, and why the average score is not as good when I have a small number of cross-validation falls? So first, the speed. Yeah. So the speed is easy because when we use CV equals 3, we do 3 resampling of the data and we train 3 different models. When we say CV equal 10, we need to train 10 different models. So usually training the model is the expensive step in cross-validation. Yes? Yes. And on top of that, when CV is 10, the training size is bigger because if we split in 10 folds, the test fold will be small. Whether if we split in 3, the test fold will be bigger, but the train fold will be smaller because they are complementary. So it can be very expensive to increase CV to a high value. So in general, we use 5 or 10. But we can see that when we increase CV, the quality of the predictions seems to be better. Can you explain this? Yes?
Well, if you have a higher CV, then you have a larger training set, and you have more data to predict on a smaller set.
Yeah, exactly. So when CV is bigger, as we said previously, we concatenate all the other folds together. So we have 9 out of 10 folds for the training set, so it's bigger, so we have many more samples. And generally, machine learning models, when they have more samples, they generalize better. And they have a higher accuracy on the test set. Yes? So when we increase the CV, the test size is smaller, so the individual evaluation of the score can have more variance, but the models themselves have less variance. So on average, we can just remember that k-fold cross-validation is slightly pessimistic, and in general, the true generalization accuracy on the full data set will be slightly better if your data is really identically distributed, which is not necessarily the case in practice. So cross-validation can lie to us if we don't have if we cannot make this assumption. But in general, let's remember as a rule of thumb that you can use CV equals 5 as a reasonable baseline, and then you can fine-tune the cross-validation if you have specific constraint in your data. Yes? Okay. Okay, so the question is about the interaction between random states and cross-validation, especially with this function cross-val score. By default, a cross-val score takes a CV object, and it can be an integer. When you pass an integer, the split is fully deterministic because it's actually using the ordering of the data and computing the false this way. if we want to shuffle the data, we can pass a specific CV object that we will see below to control the shuffling we do on the data. But the random state that we had previously was with a different function. It was with this function, train test split, and this function is doing a different kind of split where you can control the fraction of the test size. When you pass CV equals 5, the test size is always 20% of the data, because 1 divided by 5 is 0.2. So it's a different way to do cross-validation. One is deterministic, and this one is random. And because this one is random, it's doing shuffling of the data before splitting, you can control the random state. In Scikit-Learn, whenever we have a utility function or an estimator that uses randomness as part of its regular behavior, you can control the randomness by passing an argument random state. It's always named this way. So that makes it easier to have reproducible behaviors when you do analytics with Scikit-Learn. Any more questions on that? Okay. So let's move on to build richer models by using additional features. So one problem we have in the original data is the two columns, embarked and sex. They are actually categorical variables. Let me recall what we had in those two columns. Sex and embarked. You can see that in those two columns we have string values. I'll just take the beginning, the five first rows. But you can see that we have a finite number of possible values for those columns. So when we have string columns with a finite numbers of possible values, we say that those variables are categorical variables. There is a finite number of categories that the specific passenger can belong to. So here we have categories for the harbors, Southampton, Cherbourg, and Queenstown, and male or female for the sex. So as logistic regression, for instance, is only able to do numerical operations, multiplying the weights by the value of the variable, it cannot multiply a weight by the male attribute, for instance. It needs a number. So the easiest way and the most natural way to convert the sex column, for instance, into a number is to use what we call dummy variables. So we will explode the sex columns into two different columns, sex male and sex female, and we will use numerical markers, 0 or 1, depending on whether the person is a male or a female. And we can do the same for embarked. And in that case, there are 3 possible categories. So we have 3 additional columns. And the values are always 0 or 1, depending on yes? So the question is, why wouldn't we use male 1, for instance, and female 2? This is actually a very good question. So this way of representing a specific categorical variable by a specific integer value, and is for the embarked column we could have 1, 2, 3, for instance, is called using factors. Actually, there is a factorize. Let's do it. Factorize function in pandas, and this is what it does. You can see that it returns 2 things. I will put them in variables, factors and labels. Oops, I made a mistake. So the factors is a numpy array, and you see you have values between 0 and 2, 0, 1, 2. And how to decode those values, I will just take the first 10 to make that readable. Is by using the labels outcome, and you can see that 0 means Southampton, 1 means Cherbourg, and 2 means Queenstown. So Most of those people on the test on the 10 first element are from Southampton. One is from two are from Cherbourg, and one is from Queenstown. So we could use this numerical representation, and Scikit-Learn will not complain because it's numerical values, so it can do the multiplication and so on. However, it's misleading for the model because when Scikit-Learn see in a specific column integer values, it will assume that values that are close to one another in that space are also close to one another in the real space. And so it means that 0 is closer to 1 than it is to 2. So it means that Southampton passengers for Southampton are closer to passengers from Cherbourg than they are from Irish, for instance. So British are closer to French than from Irish, which is not necessarily the case. We could argue, but and depending on the way you choose the integers, you will have a different meaning associated to those integers, and the logistic regression model will use that meaning, that closeness in the integer space. So this is why we use this one-hot encoding, the dummy variables, because it means that a person that comes from Cherbourg is at a distance of 2 from a person that comes from Southampton, because the difference between that row is 1 plus 1 is 2. And you have 2 people coming from Cherbourg, from Southampton, for instance, is 1 minus 1 is 0, plus 0 plus 0, so it's 0. So you have the distance space, the distance induced by this representation is closer to the real relationship between the people. People coming from the same port are close, and people coming from different ports have a distance of 2 arbitrarily. All right, is that clear? Okay. So now that we have the ability to use the getDummies functions from pandas, we can extract the first 3 numerical columns and concatenate using pandas concat with the dummy variable representation of the sex column and the embarked column. If I do that, I get this numerical data frame, and this time I have just numerical values here. You can see that the sex female column is very redundant because with the sex male column, because they are exactly the opposite, so I can drop one of them and I won't lose anything, so I can just drop. I need to put axis equals 1 here. It's 1 or axis equals 1 to mean that we drop a specific column. It's the same. As previously, with this data frame, I still have the issue of missing values for the H column because I reused the original data. So you can see that there are still missing values in the H column. So I will do the same operation that I did previously, which means I will compute the median on the non-missing lines, on the lines with non-missing values, and use those medians to fill in the missing values. So if I do that, I get my rich features final data frame that should be clean. It just has numerical values everywhere, and I don't have any missing data. So now that I have this clean data frame with numerical values that also represent the categorical variables, I can train a new logistic regression model on the new data, rich features final, and I will compute the cross-validation score using 5-fold cross-validation. And you can see that the average score in that case is closer to 78, 79, which is much better than previously. So it means that those new features, they actually bring a lot to the predictive accuracy of the model. So let's do an exercise. So now that we have this model on this data, you can try to change the value of the hyperparameter C on logistic regression and see the impact on the cross-validation score. You can also fit a new instance of the logistic regression on the full data set. not on a specific train test split, fit it on the full data set, and plot the weights using matplotlib as we did previously, but for this new model to see the impact of the different features. So if you execute that cell, so you see the solution. So first try to do it here alone, and then we will execute that to see the solution. All right, so I give you, let's say, 5 minutes. All right, you want more time? Or? Okay, let's experiment first with the impact of the C parameter. So C is a traditional parameter in libsvm, liblinear, and support vector machine logistic regression model to control the amount of regularization. It's actually the opposite of the amount of regularization. So it means that a bigger value for C will give more freedom for the model to adapt it to the training set. Sometimes when you give too much freedom to a model, it will tend to learn the training set by heart and also fit the noise of the training set, and it's not necessarily a good thing. We'll see that later in the second half of this session. Let's just have an experimental view. So right now the mean score is around 79, let's say. Oops. And if I give it more freedom, you can see that the average score is almost the same. It doesn't change much. If I reduce this value to a positive value that is very small, you can see that the model is very much constrained in that case. And we don't have access to the individual models, but when it's constrained this way, it will basically predict a constant value. And in that case, it's predicting the majority class for all the examples. So it's very close to the rates of the constant prediction of death, basically. So if you regularize a logistic regression model a lot, it will be close to the constant prediction, basically. It's not exactly the case here, maybe because there are correlated variables, I don't know exactly. But it's good to keep in mind that when you do cross-validation, it's good to the score that you get as the output of the cross-validation is not necessarily just a representation of how good are your features or how good is the class of models that you are applying to the features. It's also reflecting how good the selection of the hyperparameters you used for the model. So to get a good cross-validation accuracy, you need good features, so good feature extraction, a good class of models, and tuned parameters. We'll see later how to automatically tune those parameters by doing cross-validation automatically and selecting the best value. So the second part of the exercise was to train a new logistic regression model on the full data set, so rich features final, and see and plot the weights. So I will not do it myself. I will just reuse the solution. So we do it exactly as previously using PLT bar. And this time we have more features than previously. So we used to have only those three weights. Now we also have the sex, whether or not the passenger is a female, and the location, the port. So you can see that apparently a female passenger had a higher likelihood of survival, and if you combine that with the price and the age, you can see so young women, rich women were the favored class of person to survive the Titanic, and it's confirmed by the film because Kate Winslet survived and Leonardo did not. But it's also maybe because children and women were given the priority to get into the lifeboats, so it might be an explanation. It could also be pure chance, but I think that in that case, if you resample the data many times, you would see that this is significant. What is not significant is the embarked port. You can see that apparently Southampton is less positive, but they are all positive. There is no port that is negative. They all have the same sign. And I think many people came from Southampton. The majority of the people came from Southampton. So we would need to resample the data many times to see whether or not they have always the same sign or not. Be careful here that we did not normalize the data. So the absolute values of those weights, they don't mean anything. So you cannot compare, for instance, age and a port, for instance, because it doesn't. Age is in years and port is 0 and 1. Anyway, All right, so the next thing that we could try to improve the model is to change the class. So up until now, we used logistic regression, which is very nice because it's very fast and it's a good baseline and it doesn't overfit much when you have low dimensional data. So we can try different, more complex models that are slower to train, but might give better predictive accuracy. So there are two different kinds of ensemble of trees in Scikit-Learn from two different kinds of families. One is bagged trees, a variant of bagged trees which is called random forest, and the other variant is gradient boosted trees, which is a class of boosting ensembles using decision trees, random decision trees. So those are in R, for instance, you have the random forest package and the GBM package, and those two packages are very successful on Kaggle, and so you can replicate that in Python using those two classes, for instance, for classification. So let's try the two of them on the same data, and we do a 5-fold cross-validation, and we compute the accuracy. So you see that the accuracy, the average accuracy is close to 91% accuracy for the random forest, and it's slightly better, between 92 and 93% accuracy for the gradient boosted classifiers. It might be just because the hyperparameters that I have selected here might not be optimal, but it's often the case that gradient boosting on low dimensional data is slightly better than random forest. I don't know exactly why, but it's empirically it can be the case. On the pro side for the random forest, they might be faster to train if you have many cores because they are easier to parallelize. Because, for instance, in Scikit-Learn you have n jobs parameter that you can put here, n jobs equals 4, for instance, and they might be faster in that case. It's not going to bring anything because it's a very small data set. But they can a random forest can train the trees individually, independently of one another, so in parallel. Whereas for boosted trees, they are trained sequentially, one after the other. Boosting means that we train a first model, we get the predictions, and we see on which samples have bad predictions, and we try to predict the errors of the previous model, and we do that iteratively, and then we average, so that the second tree is able to correct the errors of the previous ensemble. So this is boosting, basically. Whereas random forest, we train the trees independently, but we randomize them a bit, and we average the predictions at the end, and it's able to remove some of the variance of the model and get better predictions this way, but they are not trying to correct them one another explicitly. Anyway, we will see the bias variance trade-off later in more detail. So I think we are getting closer to the break, so we'll skip this exercise. So it's just that. Yes, question? We are just reusing the previous features. We are using the rich features final, so exactly the same as previously, but with a more complex model, and you can see that the score is better because for logistic regression it used to be 78% accuracy, I think, 70, and you can see that with gradient boosted trees we gained 2 or 3% accuracy for free, basically. So the question is, does it help to do specific feature engineering for random forest? Actually, random forests are very tolerant to the kind of features you throw at them. For instance, for logistic regression, we didn't scale the data, which can be very important. I've tried it on this data set, and it doesn't change the outcome very much in that case. but this is luck, so this is something that you should explore in general. But for a random forest, it doesn't care whether the data is scaled or not. So it's very robust. But the kind of features that are good for logistic regression are not necessarily good for random forest. But we will see later how to introspect what are good features for random forest. So in the exercise, there was, I will just do it quickly. One point is to try to change the value of the learning rate for the gradient boosted trees. So for instance, if I divide the learning rate by 10, it's one of the parameters, you can see that the average accuracy is not as degraded by quite a bit. So this hyperparameter here is quite sensitive. So this is when you do a gradient boosted classifier, you should adjust this parameter, at least evaluate the impact of this parameter. And usually they interact a lot with the number of trees and estimators that you put in the model. For random forest, usually you can use the default parameters and you will get reasonable results. You can improve a bit, especially if you increase the number of trees. You can increase the accuracy. So in that case, you can see that it's increasing a bit, but we are reaching a plateau quickly. So we could also try to treat the P class. Oops, sorry. The P class here, no, as a categorical variable instead of treating it as a numerical variable, because the P class has three possible values, first class, second class, and third class, and see the impact of the model. And we can also check the feature importances attribute of the model to see which of the features are the most important, the most predictive according to this specific model. So first, let's have a look at the impact of the P class. So here I'm using fair and age as numerical values. I'm extracting sex, P class, and embarked as categorical variables using the dummy variable encoding. I drop the males because they are redundant with the females. And then do the feature imputation as usual. I can train my logistic regression model in a cross-validation setting. And I can train gradient boosted trees in a cross-validation setting as well and average the score and see which model is best. And you can see that the accuracy of logistic regression by treating P class as a categorical variable might have increased a bit, but it might not be significant. And for gradient boosted trees, it did not improve at all. But we would need to fine-tune all the other parameters to be sure, but it's not very important, actually. It's very close to the scores that we got previously. But it's a good sanity check to when you have different representation for the same variable to try both and see with cross-validation what is the best features that you can extract from the original representation. Finally, to introspect the model, gradient boosted trees, when you fit them on the full data set, you can access, so here I'm fitting a new class, a new instance of the same class called gbnew. And gbnew, I can plot the feature importance attributes. Let's do it. So feature importances is something that is always positive. It's not like the coef attribute of the linear model. But it summarizes the number of times that a specific feature was used in a decision tree to make a decision, and it's scaled by the amount of impurity decrease that this split in specific trees was able to provide to the tree, and it's normalized to 1. You can actually disable the normalization. Maybe I don't remember how to do it. Have a look at the source code if you want to disable it. But just to keep in mind that this, you can actually compare the values and rank the features by importances. And you can see that the model is actually agrees with the logistic regression model that rich female and rich young female are more likely to survive. Actually, those three attributes are actually very important to make a good prediction, whereas the origin of the person and the class, if you treat them as a categorical variable, are not as important. So it's those three first elements are very important. But the class is very correlated to the fair. So for a tree, it's easier to pick one variable and to have a good purity out of it. And then once you have taken this decision with the fair, using the granular information on the class might not bring much. So because of the correlation, one might be decreased compared to the other. Yes?
Are there tools for normalized attributes in the Scikit?
So the question is, are there tools to normalize the attributes in Scikit-Learn? So yes, in Scikit-Learn preprocessing, sklearn preprocessing, you have a class called what? I was making a mistake here. You have this standard scalar class, which is a transformer. We'll see later how that works. You can pipeline it with the model to scale the data before feeding it to the model. But for trees, it's not very useful. There are alternative preprocessing routines. You can use tab completion. You can do one-hot encoding, as we did it with the pandas using get dummies, but you can also do it with a transformer in Scikit-Learn. You can compute polynomial features to combine features together. You can scale according to the mean and max values instead of using the center and the standard deviation to do the normalization. Those are the kind of utilities. You should have a look at the documentation to see the details. All right. So, yeah.
What relationships between those feature importance and the
So the question is, how do we know whether or not those feature importance are statistically significant or not, basically? So by default, Scikit-Learn does not do the computation of confidence interval, for instance. But it would be quite easy to do it. You have two options. Either you can resample the data and train new models, or you could, if you train a very large random forest, for instance, you also have a feature importance for a random forest. It's possible to resample the trees. You can adjust. Let me show you. Random forest classifier. So I will put n estimators equals 5 here. Features and target. Let me put that on top. So I will train a random forest model and put it. No. And I have also the feature importance attributes for that guy. So I could do the plot, but anyway. And in addition to the feature importances, I have also this estimator attribute here. And it's basically a list of trees, and I have access to the trees object of the forest. So I could change that list, resample the list, the element, randomly, and compute predictions and compute feature importances. Feature importances is actually a Python property. So if you change the list of estimators, this attribute will be updated automatically. And then this way you don't have to train new trees, and you could compute the variation of the feature importances on bootstrap resamples of the estimators. And then you can empirically find a confidence interval for the feature importances. Yes, there is actually a paper specifically on this feature importance by the author of Scikit-Learn Random Forest, Gilles Loup, who has studied the theory of those stuff to select variables. So if you are interested in that, you can read Gilles Loup PhD thesis. There is a chapter and point to a paper on this. All right. So you can also do that with the gradient boosted trees, but the resampling of the gradient boosted trees might not make as much sense. Anyway, so I think it's time for the break, and then we will dive into automated parameter tuning. So 15 minutes. So let's get back at a bit past 20. Let's start again. Sorry for breaking Amon Tobin. So the next part of this notebook, so the end of this notebook, is about parameter tuning. So we've seen previously that for logistic regression, we have the C parameter that controls the regularization of the model. For gradient boosted trees, we have many parameters like learning rate, max features, max depth, that might be important to adjust. And for all those models, it's really painful to do it manually and to try many times and retry cross-validation and so on. So there is a simple way to automate that tuning in Scikit-Learn, which is the grid search CV class. So what the grid search CV class does is pretty brutal. It's you give it a list of parameters with possible values. So for instance, I have this model with default values for n estimators and subsample. But for the other parameters, I will put them in a dictionary where I have the name of the parameter as a key, and as a value, I have a list of possible values. So learning rate, I will explore between 0.05 and 0.5 with 3 possible values. For max features, I will try 2 possible values, 0.5 and 1, and max depth between 3 and 4. So to understand the meaning and what would be reasonable values for those parameters, it's good to read the documentation. For instance, in general, you can just Google. Sorry. If you Google the class name of a scikit-learn models, you get into to the documentation as the first reply most of the time. And so you see the doc string formatted in a nice way. Let me make it bigger. For the possible parameters. So you see learning rate, what it means, n estimators, the default value, max depth. So for instance, max depth is the maximum depth of the individual regression trees. So the trees that we grow in the ensemble, they can take a finite, a fixed, a bound number of splits, and at some point, if they reach that limit, we stop splitting the tree into new branches, and we have a leaf node, and we make a prediction out of that leaf node. So in general, for instance, for the trees, the bigger the tree, the more flexibility it will have to perfectly memorize the training set. But then it can memorize it too much and fit the noise of the data and not generalize to new data. So there is a trade-off between the expressive power of the tree, so it needs to be big enough to capture enough of the structure of the interesting structure of the data, but not too much to avoid memorizing the noise. So you have the meaning of all the parameters. And so you can see that depth is an integer, and it's actually a positive integer because it doesn't mean anything to have a negative depth, and so on. So let's go back to the notebook. So I've selected the reasonable default values for that, and I pass them to the grid search CV. CV stands for cross-validation. I pass as first argument the gradient boosted classifier with the default parameters, those parameters. Then the parameters that I want to explore as this dictionary. I tell that I want 5-fold cross-validation to evaluate the quality of all the possible parameter combination. And the scoring metric that I will use to compare the quality of the model is the ROC AUC. and I say here that I want to use njobs equal 4. So njobs equal 4 on grid search CV will use under the hood Python multiprocessing module to split the computation on 4 different Python processes. On some versions of Python, it can cause troubles with the IPython notebook. So in case you have a crash, set it back to 1 and it will go in serial mode. Let's try it anyway because it's much faster. So this object, you can see that it also has a fit method that takes the input data as argument. So it looks like the gradient boosted classifier estimator itself. But it's actually a wrapper around it because we pass it as an argument. So we call it a meta estimator in Scikit-Learn. So it's actually something, a wrapper around a real estimator. And so let's launch the computation. And under the hood, when you launch this fit method, what it does is actually it will compute a grid of all possible combination of those 3 parameters. For instance, if it will take the value of learning rate of 0.05 with the value of max features equals to 1 and the depth equals to 4, for instance. For those 3 possible values, it will stick them into the GB object, a copy of the GB object, and it will cross-validate it using 5 folds, compute the scores, average the scores, and give that score to the parameter combination. And then it will compute all the other possible combinations of learning rate, max features, and max depth, and will do the same in parallel. And at the end, we'll collect the scores for all the explored parameters for that model, and we'll make it possible to sort the values, the scores. So here we have the GS object, which is the grid search object. We call fit on it, so it's now updated. And once it's fitted, you see that it has these attributes. In Scikit-Learn, there is a convention with the underscore here. The attributes that have an underscore means that they are computed from the data. So they don't exist unless you call fit on the model. So the coef attribute is the weights for logistic regression. It's computed from the data when you fit logistic regression. The feature importances or the estimators of the random forest, for instance, also have this underscore because they are computed from the data. And the same for the grid search. The scores for the parameters are also computed when you call fit. And so once you have done that, you can access it. So in that case, we want to sort the results. So it's a bit complex. In the next notebook, I will explain a bit more. But basically, we will sort the values by the mean validation score, and we put that in reverse order to see the best model at first. So here you can see that for the parameters max features 0.5, learning rate 0.1, and max depth equal 4, we get a mean validation accuracy of 0.7. So it's quite good, actually. It's better than what we had previously, which I don't understand because it's very similar. I don't know what I changed. Because it's almost the same. No, yeah, it's the same. I don't know. Maybe I forgot something. Anyway, so this is the best parameter combination, but you can see that you have very similar scores for many possible combinations. For instance, max features is 1, learning rate is 0.05, and max depth 4. But there are some combinations here, for instance, where the score is the cross-validation score is significantly worse. And you can see that it's mostly because of the learning rate, which is too high, because whenever the learning rate is too high, you see that the models are at the bottom. The models that have a high learning rate are at the bottom of the grid search. So we can also have a quick access to the best score and the best parameters this way. And actually, the GS object is a meta estimator, which means that it has a predict method because it will take the best model, it will refit it on the full data set, and it will be actually used to make some new predictions. So for instance, I can compute predictions on the features, and the grid search object acts as a meta estimator that wraps the best model basically at prediction time. Yes, question? Yes. Okay, so the question is about the time here. When we change the number of jobs, if I change it to 1, yeah. Okay, so I think you shouldn't trust the CPU time reported here, because in that specific case, we are using multiprocessing, which is spawning new Python processes under the hood. And the CPU time that is reported here might be just from the master process and not from the child processes. So when you use multiprocessing, you should just use that. Look at the whole time. The other times don't mean anything because it's not able to report the statistics from the subprocesses. For the random forest object, it also has an n jobs argument. And in this case, it's using Cython and it's releasing the GIL under the hood so that we can use regular Python threads instead of multiprocessing, which is better. And in that case, the CPU time should be correct. But it depends on the subprocess or not. Yes? So the question is there a way to select the number of jobs that you want to explore and get, for instance, 100 possible combinations instead of exploring all of them? And actually, yes, by using the random search CV, randomized search CV. So, oops, sorry, not here. So. Okay, so it's a different question. Okay, I didn't understand. So, okay, so I will just cancel that and I will see that later. So instead of putting njobs equal 4 here, I can put -1, and it will ask the operating system how many CPUs you have on the host. But you have to be careful because the operating system will report the logical number of CPUs, so taking hyperthreading into account. And depending on whether or not you are on a virtualized environment, like for instance on the cloud, you should divide by 2 to remove hyperthreading or not. So it's really tricky to get consistent behavior. So you can try both and -1 and divide by 2 and you see which is best. Because otherwise you might use too much memory for nothing, basically, by using too many Python processes. Another question?
Grid search the only one that works out of the box, or is there
Okay, so do we have other alternative implementation for parameter search besides grid search? So we don't have genetic algorithm, as you said. There might be a Google Summer of Code project that will start soon to implement strategies based on Gaussian processes, or maybe random forest. It's not decided yet. There is a vote happening right now about which project gets selected or not. So those could be smarter ways to do a parameter search. There is also the randomized search CV model. So let me try to use it.
how many of those sort of fitting strategies are directly useful in search strategy?
There in Scikit-Learn at the moment, I think is this. Let's see if it works. Okay, that works. So randomized search CV is a drop-in replacement for grid search, but instead of trying all the possible combination in the deterministic order, it will sample, for instance, 10 random combination and just compute the score for those 10 guys, and then you can see the results. And you can see here, so I just have 10 results instead of the full list. And in general, it's when you have many hyperparameters like this, or more than 3, let's say, it's very likely that some of the hyperparameters are not very important. And in that case, it means that by just computing 10 combination of the others, basically, you will already have a good idea of what are the good combinations. So in general, when you have a small number of hyperparameters, like one or two, it's good to use grid search because you can compute the full grid and you are sure that you are not missing something important. But when you have many hyperparameters, you cannot compute the whole grid. But it's not a problem in practice because some of them are not very important and they will not be wasted. It's hard to explain like this. I would need a diagram, but I don't have it at hand. But there is a very good paper by James Bergstra on random search for hyperparameter optimization that you should have a look at if you're interested in that topic. So it's a very good baseline when you have many hyperparameters. So in Scikit-Learn, we just have those two at the moment, and maybe more in the future. There is also a bunch of libraries like HyperOpt, for instance, on GitHub. That has this library has been written by James Bergstra, who did the paper on random search. So this is a Python library that is implementing another strategy, which is even smarter. That works with Scikit-Learn. It has a binding to work with Scikit-Learn, but to use it, you need to have a MongoDB database, and you can use a cluster to run stuff on different machines. There is also a bunch of other libraries like SMAC. I don't remember. SMAC, maybe it's not in Python, but Spearmint. Yes, this one. So Spearmint, I think it's also able to optimize scikit-learn models, although I'm not 100% sure. I haven't used it myself. But it's it's written by Jasper Snoek, who is also a researcher on this hyperparameter search topic. Oops, sorry. And so it has also like references to papers, interesting papers, and it's implementing Bayesian optimization, mostly using Gaussian process, I think. I don't remember exactly which strategies are implemented in that case. So it's also an external library. Okay. Okay. All right. So I'll just clean my notebook. Okay, so I think that's it for parameter search. Do you have more questions? No? Just want to keep... okay. So now that we did that, there is still something that is troubling in the pipeline that we implemented so far. It's the fact that we did feature imputation on the full data set, and that might actually be a methodological problem to do that in general, because here we modified the original data to impute the missing values with the median value, and then we did the train test split. In general, we should do the train test split before doing anything else, and then do feature extraction, feature imputation, scaling, and those kind of operations. Because if we don't do that, we might use information from the test set in the training part. For instance, when we compute the median, we compute it on the full training set, on the full data set. So we are using information from the test set inside, and we give it to the model before doing the split. So we might be cheating, and we don't know if we are cheating or not unless we do the proper thing. So in that case, the proper thing would be just to do the feature representation using categorical representation for the categorical variable without doing the median imputation of the missing values. And we will use scikit-learn models and a pipeline to do it properly. So here I'm using pandas. I extract the categorical, the one-hot encoding for the variables. And this time, the missing values, I will just put a marker, -1, to say that they are missing. Otherwise, I have the NA flag of pandas that scikit-learn doesn't like. So I'm just replacing that by a constant to just put a marker. And before doing the imputation, I will do the split. So I'll do the train test split using the train test split function. And I'm just fixing a random state and a split size, and that's it. So now that I have that, I can do the imputation of the missing values with the median strategy as we did before. But instead of doing it with pandas, I will do it just on a training set with this class from scikit-learn that has a fit method. So it's looking like an estimator, like logistic regression, for instance. It has a train method, but instead of training a predictive model, it will just collect some statistics on the features. And in particular, it will extract the median age on the second feature, so 29 years old, on the non-missing values. It knows that the missing values are encoded with -1. I know that I just have -1 for missing values. So it computes the median for all the possible features, ignoring the missing values. And then once I have this, so I can just display that the second feature is actually the age. And once I have this, my imputer can be used to transform the data. So I can transform the training part of the data set and the test part of the data set using the same imputation strategy, but the imputation was done just using the training part of the data. So it's not cheating anymore. It doesn't use the test set to compute the statistics. So it can feel that like nitpicking in that case, but this is the only way to know whether or not we are cheating or not. So in the original X-train data, you can see that there are some values that were set to -1, and np.any returns true if there is if this statement is true anywhere, somewhere, at least somewhere. But when I do that on the X-train imputed, which is the result of calling the transform method on the imputer on the train data, I can see that I no longer have any missing values with the -1 marker. I can do the same on the test set. You can see that there are missing values in the test set. And once the test set has been transformed, there is no more missing values. So the imputer class is implementing the transform method. So we called that a transformer in scikit-learn. So it has a fit method and a transform method, whereas the classifiers, they have a fit method and a predict method. So when you have transformers, what is interesting is that you can pipeline them with the classifier. You can put a transformer or a list of transformer and then a classifier at the end and group that sequence of models into a big model, which is a meta estimator as well, and train the model all at once. So this is exactly what we do here. We implement the pipeline class here. We create the imputer class as we did previously with the median strategy and the -1 missing value marker. Then we create a gradient boosted classifier with some hyperparameters. And we combine the two in a pipeline object. Then, once we have this pipeline object, we can compute the cross-validation on the pipeline itself. So it will do the feature imputation on each possible training fold independently of one another. And when I do that, I can compute the actual score of my model, and I see that it's almost as good as previously. So it means that we did not cheat by doing the imputation, or at least it's not important in that case. And it makes sense because the computed imputed values is 29 or 28 years old, but it's not very important. But by using this pipeline, we are sure that we are not snooping any information that we shouldn't do in a real life setting, basically. Okay, so we now that we have the pipeline, what is interesting is that we can also do grid search on the attributes of the pipeline. So, for instance, the first stage of the pipeline is the imputation. The second stage is a classifier. You can see that I have a double underscore marker here, and the name of the parameters of the imputer and the name of the parameters of the classifiers. So I can do a grid search on the full pipeline and see whether or not the mean or median strategy is the best, if it has an impact on the quality of the model. So I will execute that. Take some time. And here you can see that for the best model I have median, but for this third model I have the mean, and you can see that the score is very close. So it's likely not to be significant to use the median or the mean in that case. At the end you also have a mix of mean and median for the worst models. So it's a good sanity check when you have several stages in a pipeline for feature preprocessing, to fine-tune the parameters of the preprocessing steps in the grid search also, to make sure that you are doing the right preprocessing for your classifier. Sometimes you have a strong interaction between some parameters of the classifier and some preprocessing. So, for instance, if you extract many features, you are more likely to have a overfitting model, so you might benefit from having a stronger regularization in the classifier. So you have this kind of interaction. Anyway, all right. So we can just compute the ROG curve of the final model. And you can see that it's much better than the original curve that we had for the logistic regression, which was more in the middle. And the area under the curve is 89 almost. And we can see the best parameters for this search. All right. Finally, I just want to point out that there is this project, Scikit-Learn Pandas, that provides additional tools to make it possible to pipeline data frame operations in a Scikit-Learn pipeline to transform specific columns with specific transformers. So it might be a better way to do it in practice. It used to be an external project, but some of the modifications that were made in that external project have been included in the latest release of Scikit-Learn. There are still transformers utilities that are interesting in that project. But for instance, it used to have its own version of grid search and cross-val score. It's no longer necessary to use them. You can use the version of Scikit-Learn now because they have been fixed to work better with pandas from the start. I think that's it for this notebook. So if you have questions about that. No? Yes, one question? Okay, so basically on the x-axis you have the false positive rate, and on the y-axis you have the true positive rate. So you remember we computed those values with the confusion matrix, but we had one possible value for the true positive, for instance, right, with the confusion matrix. But what you can do is you can change the threshold of the decision function. And if you do that, you will get many different models with different false positive and false negative rates. And if you link those models one to another, you can plot that curve. And so a model that is completely random will predict the diagonal. You will be on the diagonal. A very good model will be up and right, up and left. And so if you compute the area under the curve, you have a good, it's an estimation of how good the model is on average, irrespective of the threshold value, basically. So it's especially important when you have imbalanced data. This is one way to evaluate the models. There are other curves that you could do, but this is one of the most used. I didn't get on which kind of data? Okay. Okay, so the question is, this model is doing good on imbalanced data, but are there strategies to deal with imbalanced data by rebalancing it beforehand, for instance, if the model is not able to deal with it directly? In that case, the data is not too much imbalanced because you have a 2-to-1 imbalance ratio. So most scikit-learn models will deal easily with that kind of imbalance. What is problematic is when you have 1 to 10 or 1 to 100. In that case, it might be beneficial to either subsample randomly to remove some of the majority class. What you can also do is sometimes you have parameters that have class weight attributes to the constructor, and you can say class weight equals auto, which will compute the frequencies of the classes and will put more weights on the classes that have less examples, less samples. And that might be beneficial. You can also pass arbitrary weights that you can cross-validate on grid search. If you want to grid search the class weights, you can do that also. So depending on the model, that might fix the problem or not. There is no generic solution in general to fix class imbalance. Another strategy that might be useful is to fit a simple linear model with a high precision. So you adjust the threshold to make sure that you have you can do the precision recall curve as we did here, but it's a different curve with different axes. And you can adjust the threshold to make sure that the precision is more than 99%, for instance. And use that first linear model to get rid of most of the easy negative samples. And then out of the possibly positive, you have a rebalanced subset on which you can train a more complex classifier. So you can cascade 2 classifiers this way. That might be another better way to deal with class imbalance. There is no ready-made tool to do that in scikit-learn. You can just do it yourself. Okay, no more questions? Okay, so let's move on to the next notebook. So I think we won't have time to do the 2 of them. So would you be more interested in discussing overfitting, model assessment, cross-validation, learning curves, and stuff like that? Or how to work with text classification, with text data? So who wants to vote for text data? Okay. And model assessment and selection?
I also want to.
So we'll have to split the room. Okay, so I don't know actually. I'll pick something random and be. So let's say 0 means text. Okay, so it's text. Let's try again to make sure that it didn't make a mistake. No, it's 0 and 1. Okay. No, it's the Mersenne twister. I trust it. Okay, so text classification. So it's the notebook number 7. Anyway, there is a video recording of the other chapter on the GitHub repo, you have a link to the YouTube video. So you can always follow the video for the other section. Okay, so first let's import those guys. So matplotlib and stuff. Make sure that you have the data. All right. So when we deal with text data, the original representation of the data is just a bunch of Python strings or text files on a hard drive. So it's not a NumPy array with numerical values, or it's not a pandas data frame with numerical values. So we have to find a specific way to encode the original representation into something that is a numerical representation. And the classical way to do that is to use the bag of words representation. I will explain a bit more in detail later. Once we have this representation, we can train a classifier, a usual Scikit-Learn classifier on the feature vectors that we extract. And the best way to deal with the two operations together in a consistent manner is to use a pipeline to stack the two together and to do a model selection and cross-validation of both the feature extraction and the classifier together, because they have interaction between the two sets of parameters. So we can do that. And we can do the full exercise in 20 lines of Python. So it almost fits on the screen. So let me execute that guy. So here you see that we import a utility called load files from datasets to load some data from the hard drive. We have two folders from the 20 newsgroups dataset that has been split by date. So the 20 newsgroups dataset is a bunch of posts from 20 newsgroups, so forums in the early days of the internet. And some of the posts were collected before a specific date, and the other posts were collected in the future with respect to that dataset. So we have two datasets that are really independent. If we train on the training part and we predict on the test part, we are actually predicting the future in a way, because the test part was collected after the train part. So you can see we are using load files, and it will use the folder structure of those folders to collect example documents. And we will collect only documents for specific folders. So we have 4 specific news groups that we are interested in. So one is on atheisms, one is on religion, one is about computer graphics, and the final one is on science, and in particular space and astronomy. So we collect this data. Then we will use TF-IDF vectorizer, which is the kind of bag of words feature extraction. And you can see that it's implemented as a scikit-learn class that has a fit transform method that will extract the representation and transform the data into a X array, a SciPy matrix. And once we have this representation, we can call this multinomial naive Bayes class and train it on the representation that was extracted by this TF-IDF vectorizer. And we can compute the score on the training set and the score on the test set that we generate by reusing the same vectorizer as previously. But this time we do not call fit transform, we just call transform to do the same operation that we did on the training set. We reuse the same mapping on the test set, and we can compute the score of the classifier on the test set. And here we can see that on the training set, the classifier is able to reach 95% accuracy, and on the test set, which is the real generalization of the model, it's already quite good, because it's 85% accuracy out of 4 possible choices. So it means that if you pick up a topic at random among the 4 possible values, you will have 25% accuracy by default, by random chance. So when you have 85 is significantly higher, so it means that it's actually able to guess the topic out of the pure content of the document most of the time. So this is just an overview of what we are gonna develop in that notebook. We will have a look at the individual components. And first, this is a graphical summary. So it's the same data flow as previously. But here we have text documents, and we are using a vectorizer object to extract the feature vectors using the fit transform method on the document, on the text documents. Then we can call clf.fit for the classifier with the x and the y. The y's are the labels, the topics of the post. So this is the machine learning algorithm, and it updates itself, and you get a predictive model. CLF is updated basically, and then on the test document we can call the transform method of the vectorizer to get the feature vectors, and then compute the prediction with the naive Bayes classifier. Is it clear for the data flow? Yes. So let's have a look at how it's organized. So people under Windows, you might need to get rid of that -LH to get this running. So in the dataset folder, you should have two subfolders, one for the 20 news groups test and train data. And if you have a look at the train dataset, you see one subfolder for each topic. And we have 20 possible topics. If you have a look inside one of the topic, you see many documents. And the name of the documents, they are text files with just a digit as file name. But they are text files. You can trust me. And there are many of them. And they are a couple of kilobytes each. Sometimes less than that, because they are individual posts on a news group. Oops, no, that's not what I wanted to do. Okay. So we have this folder structure, and the load files utility of Scikit-Learn is able to introspect the folder hierarchy and to load the text files as Python strings in memory using a specific encoding. So you need to know how your text files are encoded. In that case, it's Latin 1 because there are English-speaking forums from the 90s or 80s, I think. And at the time, they used Latin 1 instead of UTF-8. And we can also shuffle the data at the same time to have no specific ordering in the data sets that we load to mix the topics. And once we do that, so it takes some time because it's loading the data from the hard drive. What we get as a result is this object that looks like a Python dictionary that has keys, and you see the attributes, target names, data, target, desk, which we should be renamed to description, and the file names if you want to trace where the data comes from on the hard drive. So we can have a look at the target names first, and you see that they are matching the folder names. So this is the target class that we want to predict. The target attributes are just integers that encode the class. In Scikit-Learn, we use integers for the target variable because it's more memory efficient when you have millions of points instead of repeating many times the string representation. And if you look at the shape of this target attribute, you can see that we have 11,314 documents. And in the test set, we have a bit less than 8,000 documents. If we have a look at the length of the data attribute of that data set, it's actually matching the length of the target attribute because we have the same number of documents. But the type of those objects are Unicode Python strings, Python Unicode strings. So depending on if you're on Python 2 or Python 3, on Python 3 you will get str. Here I'm using the old version of Anaconda. I'm using Python 2, so I have Unicode. But Python 3 str string is the same. It's almost the same as a Python 2 Unicode object. It's decoded data. So we can use this function display sample as a quick utility to see, for instance, the sample number 0, the first sample of this data set. It has the class ID 12, which matches the electronics news groups. And if we have a look at the text content of that document, we see a bunch of headers, like email headers. So we have a from, we have the email address of the poster, we have the subject line, and sometimes we have the organization. At that time, it was people posting to the mailing list. The news groups were mostly people from academia, because this is where internet was available. And you also have the body of the text. And sometimes you have a signature using the -- symbol. So the goal here is to predict the topic from the body of the text. So from the words of the body of the text. So we can have a look at the second example. And in that case, it's a miscellaneous for sale ad. And this person is selling, I don't know. I can't see it. Anyway, they are speaking about random stuff. Anyway. So we know that we know the char set. We are using a Latin 1 char set, so we know that it's using 8 bits per character. So if we can encode actually the data and multiply it by 8 and 1 million, and we'll have the size of the training set and the test set in megabytes. So just to have an idea, this is a bit less than a bit more than 200 megabytes total, almost 300 megabytes total. So instead of working with the full data set to make the notebook run faster, we will use just a subset where we have just those 4 classes instead of the 20 classes. And in that case, we just have 31 megabytes for the training set and 22 for the testing set. So we want to extract the feature vectors from this raw text representation of the dataset. So to do that, we will use the TF-IDF vectorizer. So TF-IDF stands for term frequency inverse document frequency. It's a way of computing numbers that represent the frequency of individual words in a document. So the bag of words representation will basically split a string of English words, for instance, into individual words. And for each token, each individual word will map it to a dimension. For instance, the word the will be mapped to dimension number 0. The word cat will be mapped to dimension number 1, and so on. And each possible word will have its own dimension. And when a document has the word the 3 times, it could store 3 in the dimension 0. And if it has cat one time, it could store 1. And for all the other words where they are missing from this specific document, we could store 0. So this is one way of doing bag of word representation. The TF-IDF vectorizer is slightly more complicated because instead of just counting the words, it will apply some weighting to discount for the frequency of non-informative words. Maybe I'll explain that into more details later. So this TF-IDF vectorizer will do this operation, and it takes a bunch of arguments. So many parameters. By default, I will just use the default values, but maybe I can show you this. The token pattern argument is the regular expression that is being that is used by the model to extract the location of the words. So it's basically extracting sequences of at least 2 characters that are not word boundaries in Unicode. So it will use that to tokenize the text, and then it will count the number of occurrences and map them to dimensions. So the min df here means that we will count all the words that appear at least once. In some version of Scikit-Learn, the default value is min df equals 2. You can change this value. It means min df equals 2. It means that it will ignore words that appear only once in the full data set, and will keep only words that appear at least twice. That makes it possible to clean up a bunch of garbage that are just unique identifiers, for instance. Let's try with one for now to be able to introspect how it works. So we have this fit transform method. We call it on the list of Python strings from the small data set, so with the 4 categories. And what we get as a result is this xtrain small data structure. You can see that this operation is quite fast in Python. So it processed, like, I don't remember how many, couple of thousands of documents in 800 milliseconds. So it's quite fast. So just to give you an idea on the speed. So the resulting object that we get as xtrain small is not a regular NumPy array. It's a different kind of data structure, which is called a SciPy sparse matrix. And you can see that it has a shape. It has a shape attribute like a pandas data frame or a NumPy array. And the first dimension of the shape is the number of documents, so 2000 in the training set. It's matching the number of strings that we had originally. And the number of features is the number of unique words that it could find in this training set. So in those 2000 documents, it could find 34,000 unique English words. And there are some stuff that are like weird names, like email address components and stuff like that. Whatever matches the regular expression of the tokenizer. So we can have a look at this attribute of the vectorizer, which is called the vocabulary. It's a Python dict, and it has the same numbers of elements as the number of features in the sparse matrix that we get. And the keys of that guy, let me add a new, I can do keys. I can put it in a list to make it work in Python 3. And I can take the first 10 elements. Oops. I forgot to use the vocabulary here. And you can see the keys of that vocabulary object are the English words that have been found in the document. So in Python, the keys attribute of a dictionary, they are not ordered, so it can be random words. I think if you execute it several times, it's always the same, but it might change depending on the version of Python that you get. So those are basically, this vocabulary object is a mapping between the words and the dimensions. So for instance, if I take these words, Tilton, whatever that means, MB, vectorizer.vocabulary, I can access it, this way. And it is mapped to the dimension number 30,915. Okay? So I can also access the feature names in a deterministic order using this guy, vectorizer, get feature names. And it's actually ordered in a lexicographical order. So if you take the beginning, you see a bunch of chunks with digits, 0 digits at the beginning. If we take a slice in the middle, if I divide the number of features by 2 and I take 10 samples in the middle, so I get regular names. So this is basically the keys of the vocabulary, but in a deterministic order. So this vectorizer has tokenized the text of the training set, identified all the possible unique words, ordered them, and assigned them a specific dimension to all of them. So once you have this, you can call the transform method and project the original string data into some scikit-sparse data structure. So just to say a couple of words on the scikit sparse matrix data structure that we have here. So why do we use this data structure instead of a NumPy array? If we were to store this NumPy array as a NumPy array, actually we can do it. We can call toArray here, and that might crash or not. Like it's small enough to not crash. But if we convert it into an array, we will have an array with many zeros, and from time to time a value that is a non-zero. But it's completely stupid to store a big data structure with that large number of dimensions just to store zeros most of the time. So instead, we are using this scikit-sparse matrix, which is a compressed sparse row format that is actually just storing the integer indices of the non-zero values, like the column and the rows and the values of the non-zero values, and it's implicitly assuming that all the remaining values are zeros. So it's much smaller in memory, and it's much faster to process because we can skip the zeros for many algebraic operations. Okay. So once we have this, we can represent. We can do a graphical representation of our data set using the truncated SVD unsupervised model of Scikit-Learn. So truncated SVD is a bit like PCA, but it doesn't try to center the data because in that case we don't want to remove the zeros to be more efficient. So if you remember, if you were there this morning at Jake's presentation, we were using PCA to do a 2D representation, a 2D projection of the data set. Here we can do a 2D projection of the data on two interesting axes, which are the singular vectors of the sparse matrix. And we can use a scatter plot with different colors for different classes. And we have this representation. So it will find two axes in that space, and will project the data into those two axes. Yes? So basically, I'm calling scatter plots for different values of I, and I is the unique values of Y train, and Y train are the target variable. So the classes. So it can be between 0 and 3, and they match the target names. I don't remember the name of the variable. Actually, it's there. The possible values of the targets are those classes. So 0 means I SEA them, 1 means graphics, 2 means space, and 3 means religion. So I will iterate over the possible values of Y, so between 0 and 3, and I will cycle on the possible colors. So I just over-allocated some colors to be able to change the number of classes and still have this code that work. And then I will do a scatter plot only for the samples of that specific class. For instance, I SEA them. And I will take the first column and the second column of the projected data according to the PCA. It's not a PCA, it's a SVD, but it's almost the same. Yes? It's just a mask. It means select the samples where the Y train attribute is 0, which means atheism, or is 1, which means graphics. A NumPy array with Boolean attributes. It's a mask. You cannot slice because Y train, you see the ordering of the values, it's shuffled. So if I say Y train equals 1, I will have true for the first one, false for the second, and so on. And if I say 2, I have a different mask. So I can mask the data according to the class. So if I mask my xtrain array on the rows, this will mask the rows based on the class, and the columns will be 0 or 1, the two SVD components.
So the index operator is overridden to take a mask of an NumPy array that serves as an ask?
You can mask an NumPy array by another NumPy array. For instance, NP range 5. Okay. If I mask it by NP, I don't have any good example here. A equals 1. So if I compute a mask like this, A equals 1, I'll put you can see that this mask is true here and it's 0 everywhere else. If I take A of that, I get just 1 because I just get the matching entry. So it's a bit trivial case in that case. It's basically masking with a Boolean array. Yeah. But you can do. Yeah, so you can do indexing with arrays of integer indices, but you can also not slice, but mask an array with an array of Boolean values, true or false. And if it's true, it keeps the value. If it's false, it just discards it. And in the resulting this data structure, you don't get the false rows in that case. Anyways, just to call the scatterplot function with different colors for the different classes, basically. This is what it does. So all the blue points, the dark blue points, are documents from atheism projected into that SVD space. And you can see that the light blue, I think it's cyan, are for religion. Space is red and computer graphics is green. So you can see that there is a region of the space here where you have an overlap of many possible classes. So there are some documents, maybe they are very short and they have maybe not necessarily very interesting words, and they are projected in the same region of the space. But there are some documents who are very specific of their class. For instance, here you just have red elements. So you can assume that this region of the space is very specific to science and to space. And you can see that the two, atheism and religion, they are very much overlapping in that projection. And it kind of makes sense because the kind of words that you use to speak about atheism, which is the absence of religion, are also the same as the words that you would use set the test document into a SciPy sparse matrix using the same vectorizer. And once you have the SciPy sparse matrix for the test a subset, we can check that it's a sparse matrix as well, with the same number of dimensions. We can make a prediction, and in that case, it's close to 90% accuracy. I don't know why it's different than previously. Maybe because we changed the value of alpha. So we can also compute the score using the score method on the training set, and you can see that on the training set, it's very close to 1. So there is a difference between the score on the test set and the score on the training set. As usual, it's much easier to do a good score on the training set because you can just remember what you saw during training and output that as a prediction. So the difference between the two is the amount of overfitting of the model, which is explained in the last notebook. What is very important is to measure the score on the test set. Okay, let's have a look at a bit more details on how the TF-IDF vectorizer work. So to understand the values of the parameters, you can have a look at the docstring. So here, because of the resolution of the screen, the formatting is a bit messed up. But as usual, if you do that and put that in Google, you have the formatted version, which is more readable for the meaning of the individual parameters. So there are many of them. I won't explain them all. We will just study empirically some of them. No, it's not this screen, sorry. I'm lost now. Okay. Let's skip that. So first, what we can do to understand how the vectorizer works is called this public method, which is specific to the vectorizer, the TF-IDF vectorizer, which is the analyzer, which is a sub-object used by the vectorizer internally, that is used to truncate the strings, the documents, into tokens. You can also call it a tokenizer, but it's actually slightly more complex than a tokenizer. I don't know if some of you have experience with Lucene, Solr, and Elasticsearch. The same kind of components. The analyzer is a tokenizer and does additional filtering on top of that, and it can also extract n-grams, which are called shingles in Elasticsearch. It also gets rid of stop words. For instance, it can get rid of stop words. I don't remember if it does so by default. In that case, you can see that the I love Scikit-Learn. This is a cool Python lib. There is the I words and the A words that have been filtered out because they are single letters words. And most of the time, when you tokenize a document with, there might be like characters that have nothing to do with words, so it's a reasonable default to get rid of them. They are not very informative anyway. But here you can see that we have a problem because the default tokenizer treats Scikit-Learn as two different words, scikit and learn, and we don't speak about learning directly in that sentence. So you might want to treat the hyphen sign as a word character. So what you can do to change that is change the token pattern, the regular expression that is used by the analyzer to tokenize, and the text preprocessor by default it's converting the text into lowercase to reduce the number of possible dimensions. So let's put the no-op lambda instead, the identity function, and call the analyzer again. And you see that this time we have all the words. We didn't restrict ourselves to words with 2 letters, so we can just use a 1-letter word. And this time Scikit-Learn has been treated as a single token. And you have capital letters treated as separate tokens also. So you can customize the vectorizer parameters this way. There are many more parameters, and you can use the build analyzer on a specific example to see how it works. What impact does it do on a specific Python string? So it's a good way to debug the hyperparameters to really understand what it's doing under the hood. So I don't remember what time are we supposed to finish. It's supposed to be over. Okay, all right, almost. So we won't have time to do the exercise. I can just show the pipeline because that's quite important. Once you have a vectorizer and a classifier, here we change to a different classifier. You can combine them in a pipeline, and you can set the parameters of the vectorizer, and you can cross-validate the whole pipeline at once this way, as we did previously. So here I'm computing the mean score and the standard error of the mean across the cross-validation folds. And once you have this pipeline, you can do grid search as we did previously. and select the best value for the parameters of the vectorizer, and see the impact of the feature extraction parameters on the final score of the best model by doing a grid search on the pipeline object. So this can take some time, and at the end, I should see the best parameters, so it takes some time. Okay, maybe I should have tried with a simple less parameters. Here, just want to explain that we have the n-gram range. N-grams means that when it's equal to 1 and 2, it means that it will consider as dimension individual words and sequence of 2 words. For instance, if you have a document with New York is a nice city, for instance, New will be treated as a word, York will be treated as a word, and New York will also be treated as a word. So that's useful sometimes to extract bigrams and not just unigrams as individual tokens. Okay, so at the end, by doing so, you can see that the best model that we found with the grid search did not use bigrams because the range is between 1 and 1, so it's just unigrams. It decided to use IDF, which is the kind of weighting. But anyway, I think on this small data set, it's not very significant. On a larger data set, using bigrams would have been beneficial, I think. Finally, we can also introspect the model. And in particular, what is interesting is that we can extract the coefficients of the classifier and the feature names of the vectorizer and see for what is the word that match a feature that has a strong coefficient, either positive or negative, for specific classes. So it's a good way to understand what is doing what is happening under the hood with the combined model, the vectorizer plus the classifier. So here, this is a function that does that does a text representation of that. So for the class atheism, the coefficient for the word atheism itself is very strongly positive, whereas the coefficient for the word space or for the word graphics or for the word Christian are very strongly negative. Yes?
Did the text actually include atheism?
Yeah. So actually, in that case, we are a bit cheating because we have the sometimes the subject line have not always, but sometimes it has the name of the news group, and sometimes it's in the signature, or sometimes it's in the email address, or they are very informative. So, for instance, there are stuff that are university names that appear in the features, like Caltech, for instance. It's not because Caltech is strongly related to atheism. It's because there is one person from Caltech who is very active on that forum. So this means this kind of stuff is very useful to introspect manually. And in that case, the exercise was to strip the headers and to strip the signatures to get rid of that kind of leak data that isn't supposed to be there. So you can do the exercise and there are the solutions. And if you do that, you can get rid of those strong features. So you can have a look at the other classes. And for instance, for religion, we have Christian and beast and abortion and stuff like that. Terrorist for some reason. And essayist is strongly anti-correlated. And you can see that graphics and NASA are also strongly negatively correlated. This is because we just had 4 classes in this data set, but it's very likely that if you also had an additional class, like a junk class, like unknown topic, with random documents from scraped from the web or from Wikipedia, those strong negatives will disappear. This is another exercise, but you would need to collect Wikipedia data to check that it works. But it's a good practice in general to add an additional class when you do text classification with random documents that you collect outside of your domain of interest to model the stuff that is not of interest, basically, explicitly. So that you have probabilities of interesting classes that mean something. They are normalized against unknown stuff, basically. All right. So I think that's it. Thank you very much for your attention. And if you want to have a look, you can watch the videos. So. We'll be at the conference till the sprints, to sprint on Scikit-Learn also next week. So if you're interested in participating at the sprints.